All right, let's jump right into this. Today, we're diving into the absolute core of coordinate geometry, specifically zooming in on straight line graphs. Now look, if you've ever stared at a graph and felt just a little bit lost, or maybe you're just trying to lock down your foundations for more advanced math, you're in the right place. We're going to take a journey together, starting from the absolute simplest concept, a single dot on a page, all the way up to mastering the algebraic equations that control these straight lines. And we're going to break it all down visually so it just clicks. Let's get started. So I want you to completely shift your perspective for a second. When you see a straight line drawn on a grid, what's actually there? For most of us, it's just ink on a page, right? Just a simple bridge connecting point A to point B. But I want you to think of a straight line as having its own specific, totally predictable genetic code. It's literally like human DNA, but for math. This mathematical DNA dictates every single thing about that line: how steep it is, where it starts, how it behaves around other lines, the whole shebang. Today, we're extracting and decoding that exact DNA.
Okay, here's our quick roadmap for the breakdown. First, the geometry of a point. Second, calculating the gradient. Third, the line's DNA. Fourth, parallel and perpendicular lines. And finally, distance and midpoints.
Section 1, the geometry of a point, starting from 0. Before we can build a massive, sprawling straight line, we've got to understand the absolute smallest building block. To pin down a point in two-dimensional space, we use a coordinate pair. You'll see this written as x, y, sitting inside parentheses. Think of this as a highly precise GPS address relative to 0, which we call the origin. Through that origin, you have two intersecting axes. There's the horizontal x-axis, running left to right, and the vertical y-axis, shooting bottom to top. So if we have a point at the coordinates 3, 2, it just means we walk 3 steps horizontally along the x-axis and climb 2 steps up the y-axis. It's an incredibly simple but perfectly precise mapping system.
Section 2, calculating the gradient, measuring the slope.
Okay, so what exactly is a gradient? Well, it's really just the mathematical word for slope. But the absolutely crucial word to remember here is constant. The gradient of a straight line never, ever changes. Literally, it doesn't matter if you're measuring a microscopic 1-inch segment or a line stretching across a mile. That slope value is identical. To find it, we just look at the vertical distance between any 2 points on the line and divide that by the horizontal distance between those same 2 points.
So how do we actually calculate this in practice? It's literally 3 simple steps. First, pick any 2 points on your line. We'll call them point 1 with coordinates x1 and y1 and point 2 with coordinates x2 and y2. Step 2, figure out your vertical distance by subtracting your y coordinates. That's y2 minus y1. Step 3, find the horizontal distance by subtracting your x coordinates. That's x2 minus x1. Finally, just divide that vertical change by the horizontal change. So for example, if you've got point A at 2, 3 and point B at -1, -3, your vertical distance is 6, your horizontal is 3. 6 divided by 3 gives us a nice, clean gradient of exactly 2. And since it's a positive number, it means our line is sloping upward from left to right.
Now check this out. This is where the math really starts talking to us through patterns. Look at this simple table of coordinates taken from a line. Point A is 1, 2. Point B is 2, 4. Point C is 3, 6. Are you seeing the relationship there? Every single y coordinate is exactly twice the size of its x coordinate partner. Just by spotting that super simple relationship, we instantly know the equation of this entire line without doing any heavy lifting. The secret rule all these points share is simply y equals 2x. Section 3, the line's DNA, the algebraic code. Okay, drumroll please. Behold the master equation y equals mx plus c. Seriously, if you only remember one single thing from this entire explainer, let it be this formula. The letter m is our gradient, that steepness we just figured out how to calculate. And the letter c, that's our y-intercept. That is the exact specific spot where our straight line crashes through the vertical y-axis. When you see an equation in this format, you instantly know how steep the line is and exactly where it starts, completely skipping the need to physically draw it out. But you know, sometimes math likes to play hide and seek with that DNA. You'll often run into equations that look messy, taking the general form ax plus by plus c equals 0. It looks kind of intimidating, right? But it's actually a super easy fix. First, just use basic algebra to shuffle the terms around and isolate y on one side of the equal sign. Second, divide everything by whatever number is sitting in front of y. You want y totally by itself, meaning a coefficient of 1. And boom, you've hacked it. You're right back to our beautiful, clean y equals mx plus c format, and the line secrets are totally revealed. Section 4,
Parallel and perpendicular lines, relationship rules.
Let's put two different lines on the same graph and see what happens. On side A, we've got parallel lines. By definition, they have the exact same slope. If line 1 has a gradient of 3, line 2 absolutely must have a gradient of 3. Think of them like identical twins walking side by side forever. They will stretch into infinity and literally never touch. Now on side B, we have perpendicular lines. These guys crash into each other at a perfect 90-degree right angle. And their rule? They have what we call negative reciprocal gradients.
So, the magic number you absolutely need to remember here is -1. If you have two lines that are perfectly perpendicular and you multiply their two gradients together, the answer is always, without fail, exactly -1.
Let's actually see that rule in action, because it's pretty brilliant. Say line A has a gradient of 2. What's the gradient of a line perpendicular to it? Well, we take the number 2, we flip it upside down to make it a fraction, so 1/2, and we slap a negative sign on it. That makes line B's gradient -1/2. Now multiply 2 by -1/2, and what do you get? Precisely -1. It's a totally foolproof mathematical test to prove that two lines form a perfect 90-degree cross.
Section 5. Distance and midpoints, measuring the line segment. All right, we're shifting gears slightly to measure the actual physical distance between 2 points. And to do this, we're going to call on an ancient mathematical friend. Measuring distance on a coordinate grid is literally just Pythagoras' theorem wearing a disguise. Think about it. If you plot 2 points, say 1, 3, and 5, 6, and connect them, you can drop a vertical line down from the top point and a horizontal line across from the bottom point. Instantly, you've built a right-angled triangle, and your straight line is just the hypotenuse. And from that visual, we get the official distance formula. It is a direct mirror of a squared plus b squared equals c squared. Step 1, find the horizontal distance, just the difference between your x coordinates, and square it. Step 2, find the vertical distance, the difference between your y coordinates, and square that. Step 3, just add those two squared numbers together and hit the square root button on your calculator. Just like that, you've got the exact physical length of your line segment. But what if you don't care about the total distance and you just want to find the dead center of that line segment? Well, the midpoint formula is wonderfully simple. To find the middle, you're essentially just finding the average. You take your two starting x coordinates, add them up, and cut them in half by dividing by 2. Then you do the exact same thing with your y coordinates. Add them up, divide by 2. Put those two new numbers together, and you have a brand new coordinate pair sitting directly in the exact center. Super intuitive, right? Wow, okay, we've covered a ton of ground today. I really want you to take a mental snapshot of this toolkit right now. You've got your gradient formula to figure out steepness. You have the ultimate universal DNA equation, y equals mx plus c. You've got your distance and midpoint formulas to measure out those physical line segments. And of course, your golden rule for proving perpendicular lines. These 5 mathematical tools give you absolute, total mastery over straight lines on any 2D grid. And that essentially wraps up our explainer. By taking the time to really visualize these structures today, you've taken abstract numbers and turned them into real, measurable geometry. You officially hold the genetic code of straight line graphs in the palm of your hand. So my final question for you is this. Armed with this incredible geometric toolkit, what mathematical mysteries are you going to decode next? Keep practicing, keep trusting the structure, and we will see you in the next explainer.